Gnanam Paramam Dheyam. Knowledge is supreme.
Okay, welcome back. So before the break, we saw that the relationship between stability analysis and feedback control is very interesting. So feedback control we typically use to have a disturbance rejection, and it is our idea that when we implement the control system, it will be able to reject that disturbance, or it will allow us the ability to move the system from one point to the other. But we saw through that example of 3 CSTR that the feedback control also has a tendency that if you use a wrong value of controller parameter, it can actually destabilize an originally stable system. So it is very important that you know what are the bounds up to which you can vary the controller parameters, and that will be possible by doing stability analysis of a feedback system. So this stability analysis can be done using Laplace domain analysis or frequency domain analysis. So we will start with the Laplace domain analysis, because already we have studied the transfer function in the Laplace domain for a feedback system. So let us see how we can use that information to assess stability of a feedback system. So in week 3 we had seen what do we mean by poles or zeros of a system, and that time we had made a comment that if all the poles of the system lie on the left half plane of the complex plane, then the system remains stable, in the sense that the system has decaying oscillations or it decaying exponential, so that the system goes back to the original point, or the deviations are limited. The system does not grow out of proportions, as against if the poles are on the right half plane, or any of the poles is on the right half plane, the system either has growing oscillations or a growing exponential, and eventually the system will go towards instability. So in terms of stability, so if we are doing Laplace domain stability analysis, the key feature which we are going to use is if all poles of the system, it may be open system or a closed loop system, are in left half plane, the system is stable. Or a correct more improved definition can be that if any pole of the system is in right half plane, the system is unstable, because this particular statement does not include if the poles are on the imaginary axis, in which case the system has sustained oscillation, and when the system has sustained oscillation, the system kind of remains marginally stable, because the system oscillates around the steady state. It is not going too far away from the steady state, because we can always say that the bound is same as the amplitude of the oscillation, and because of that these systems are stable. If you include the imaginary axis, system becomes marginally stable, except if the pole is at origin, which is an integrator and an unstable process. So a more correct definition would be if any pole of the system is in the right half plane, the system is unstable. So all we are interested in terms of assessing the stability analysis, doing stability analysis in the Laplace domain, is to find a pole and see if all the poles, if any of the pole lies on the right half plane. And if you recall, how do we get poles of the system? So poles are the solution of an equation ds equal to 0. This also we known as a, it's also known as a characteristic equation. So we write the transfer function of the system. So if gs is the transfer function, we write it as ns over ds, and we take the denominator polynomial equal to 0, and the roots of that polynomial will tell us the poles, and depending on the pole we will know what is, whether the system is stable or unstable. So same logic we will be using in order to assess the stability of a feedback system. So when we were talking about a feedback system, we have already derived these transfer functions in servo or regulatory mode. So if we are talking about feedback system, then in the regulatory mode, the transfer function we had derived was gd over 1 plus gp gc gv gm. In the servo mode, it is gp gv gc over 1 plus gp gc gv gm. And here we will at least start with the fact that gd is stable or gp is inherently stable. So if that is the case, or we just need to make an assumption that this disturbance transfer function is stable. So it is not going to add any unstable pole into the characteristic equation. If that is the case, so gd is stable, that is poles are in the left half plane, then this transfer function is already in ns over ds form, and the characteristic equation becomes 1 plus gp gc gv gm equal to 0, which is same for regulatory or servo. So this is the equation which we have to monitor, which also has gc in it, which will be a function of controller parameters. So using this equation, we would be able to find out whether the system is stable or unstable. So let us now try to find out the characteristic equation for the 3 CSTR system which we had just seen. So for the 3 CSTR system, we had the process transfer function as 1 over 8 s plus 1 cube. We have used a proportional controller, so GC is equal to KC, and we can assume that the measurement dynamics are instantaneous, they are reliable, and we can also consider the wall transfer function to be 1, and in that case the characteristic equation becomes one plus Gp Gc Gv Gm equal to 0. It means 1 plus 1 over 8 s plus 1 cube Kc 1 and 1 equal to 0, which you can simplify and get, it will be s cube plus 3s square plus 3s plus 1 plus Kc over 8 equal to 0. So this is our characteristic equation. So you can see that the characteristic equation includes this controller parameter. So the poles are function of the controller gain. So that is how the controller gain has an effect on the stability or instability of this system. So all the poles, some of the poles of this system would depend on the controller gain. So now here we see a point that we have reached a cubic equation which will have 3 poles, and we will have to solve this analytically for different values of Kc in order to assess whether that particular Kc value is stable or unstable. So the Laplace domain analysis can become tricky and numerically time consuming. So in order to simplify this, especially the techniques were developed almost about a century ago, when the digital computers were not there to assist in terms of finding the numerical solution, or in general all the analytical solutions of this kind of higher order polynomial systems. So the researchers at that time came up with simplified methods in order to assess the stability, or what we are interested in this particular system is that all we are interested in to know that the poles of this system do not lie in the right half plane. So as long as we can ascertain that, irrespective of the value of the pole of the system, we can tell whether the system is stable or unstable. So in summary, we are just interested in finding out what is the typical range, or whether the poles lie on the right half plane or the left half plane. So in order to do that, there is a simple method which was there is a simple condition set of conditions which were developed about a century ago by two scientists known as by the name Routh and Hurwitz. So we will see how, what is that method and how it can be applicable here. So that avoids us, that eliminates the need to solve these polynomial systems in order to assess stability. So these are two conditions which will help us in terms of deciding whether the closed loop system is going to be stable or unstable. So the first condition is a necessary condition for stability. So this has to be satisfied, and this was given by Hurwitz. And these conditions are defined for a characteristic equation of the form a n s raised to n. So nth order polynomial in S where a n is greater than 0 or a n is positive. So for a characteristic equation of this particular form, the necessary, it is in order for this system to be stable, the necessary condition is that all these AIs are positive. So all this A1, A2 all the way up to AN, all these should be positive, then only the system can be stable. If any of those are negative, the system will be unstable, and if any of those are 0, then this condition cannot, this particular analysis of the Routh-Hurwitz criteria cannot be used in that particular system. The system may be stable, the system may be unstable. And let us say if all these coefficients are positive, which most of the times would be the case, then we need a sufficient condition for stability, which was given by Routh, and that condition is all the entries in the first column of the so called Routh array are positive. So in order to apply this sufficient condition for stability, we have to compute something known as a Routh array. So we will see how to construct a Routh array for any characteristic equation of this form. we have a n s raised to n so the root array, the first row of the root array will designated by R1, it will include all the alternate coefficients of this polynomial equation in S starting with the highest power. So, we will start with a n. So, the first row will include a n and then all the alternate entries from that. So, after a n it will be the entry with s raised to n minus 2, then s raised to n minus 4 and all the way up to whether it will be a n, a 1 or a 0. And the second row will be the remaining coefficients. So, we will start with a n minus 1, a n minus 3, a n minus 5 all the way up to a 1 or a 0 depending on n is even or odd. So, all the coefficients inside this characteristic equation are represented in the two rows by taking the alternate coefficients. And depending on the order of this particular characteristic equation, we will have multiple columns. This is column 1, 2, 3 all the way up to let us say n minus n by 2 column. And if you go back to the condition of root, it says all the entries in the first column of the root array are positive. So, even though we are constructing this entire matrix of multiple rows and columns, in the end we are going to be interested only in this column 1. So, we have populated the two rows of this root array by using the coefficients of the characteristic equation. Let us now see how do we populate the remaining entries of this root array. So, this first entry of this R3, let us call it as A31 and this A31 can be calculated as the negative determinant of this system. So, the determinant of this system will be a n minus 3 minus a n minus 1 a n minus 2. So, this R3 is actually a negative determinant. So, it is a n minus 1 times a n minus 2 minus a n into a n minus 3. So, it is actually negative of this determinant divided by this entry a n minus 1. So, that is how we will define A31. Then we look at A32, it will be a similar procedure, but now the matrix we will be focusing on will be this. So, it will be now a n minus 3 into a n minus 4 minus a n minus 2 a n minus 5 divided by a n minus 3. So, that is how all this third row will be populated, and wherever let us say we reach this particular point, in order to form this determinant we will have to consider these other entries to be 0. So, automatically this entry will also become 0. So, every time we finish two rows we will be reducing the number of columns which has non-zero entries. Then we look at row 4, and all these subsequent calculations are very similar. Now, when we are calculating the first entry of R4, let us call it A41, that will be given by the corresponding negative determinant of this. So, it will be A31 times the small a n minus 3, A32 times a n minus 1 divided by A31. So, these calculations will be repeated subsequently, and we will keep on reducing number of zeros. Every 2 rows one of the columns will become 0, and all the way we will return some value as r n or r m will be a m 1. After that, all the entries below will become 0. So, that way progressively we can calculate the Routh array, and in order to apply this condition of stability, what we will be doing is we will be focusing on this particular first column, and if all the entries in this first column are positive, then the closed loop system is stable. If any of those entries is 0, then this particular method fails, or it is not able to assess whether the system is going to be stable or unstable. And if any of those entries is negative, then the system, closed loop system, will be unstable, because one of the poles will be on the right half plane. So, let us now try to apply it to the 3 CSTR example. So, for which the characteristic equation was s cube plus 3s square plus 3s plus 1 plus kc over 8 equal to 0. So, the first row of the Routh array will be this coefficient, which is 1, and then the alternate one, which is 3, and there is nothing else after that, and the second row will be starting with this 3 and then this 1 plus kc over 8. This is column 1, this is column 2. Now, before proceeding, we did not look at what is the Hurwitz condition. So, for this particular system, the Hurwitz condition says that all the coefficients should be greater than 0, which means 1 plus kc over 8 should be greater than 0, and which is typically satisfied as this is a reverse acting controller. So, kc greater than 0 is typically the value which we select. So, automatically 1 plus kc over 8 would always be greater than 0. Now, let us look at how do we populate the remaining rows. So, let us say row 3 will be 3 times 3, which is 9, minus 1 plus kc over 8 divided by 3, which comes out to be 8 minus kc over 8 divided by 3, and then the other entry will be just 0. And when we go to row 4, it will be this particular matrix 3, 1 plus kc over 8, 8 minus kc over 8 by 3 and 0. So, that last entry will become 1 plus kc over 8. So, based on the Routh's array, the stability condition says that all the entries in this column should be greater than 0. So, this is automatically satisfied by the Hurwitz condition. So, the only additional condition which we are getting for this system is 8 minus kc over 8 should be greater than 0, which means kc should be less than 64. So, the stability condition on this particular system is that the controller gain, if I am using a proportional controller, should be less than 64. So, if you recall, or if you go back in the video and previous video and see the plots for which I had shown you the responses, one was kc equal to 50, where we had decaying oscillations, and one of the plots was for kc equal to 70, where we had the growing oscillation, which was unstable. If you plot it for kc equal to 64, actually you will find that it is the stability limit at which you get the marginal stability. So, we will take a short break here, and when we come back, we will look at other method of finding this stability limit rather other than using this Routh-Hurwitz criteria.